Hello students, I hope the first lecture on atomic structure that spans over 3 sections, 20 over pages isn't too daunting. So right now we are going to move on to the second lecture. The second lecture is shorter because it spans only 10 pages and we are looking only at 2 sections. Okay, so the first section we're looking at section 4 on periodic trends in atomic and ionic radii. If you refer to it and look at the syllabus document is actually on section 5. Okay, so we are covering 2 sub-objectives. That is, you are required to describe and explain qualitatively the general trends variation in atomic. Okay, so we have atomic, ionic, and first ionization energy across a period. Yeah, so this is the first time you are hearing this term, shielding and nuclear charge. Yeah, so over here the shielding, we are looking at shielding effects. Yeah, so the nuclear charge essentially is determined by the number of protons you have in the atom. Okay, and you are also supposed to describe and explain qualitatively the general trends and variation, okay, down a group. Okay, so we are supposed to explain it down a group. That would be focusing on the increasing number of electronic shells. Yeah, so over here we are looking at the principal quantum shell, and also a combination of shielding and nuclear charge. Okay, so be very clear about the objective so that when you read through the lecture notes on your own and when you are performing your revision, you are clearer what is required of you. Okay, yeah, so there are 2 fundamental considerations. That is the number of principal quantum shell. So why is that the case? Because this determines the distance of the outermost electrons from the nucleus. Yeah, we are not talking about absolute distance, we are talking about the average distance. Because on the average, if, for example, if the valence shell is found at principal quantum number 5, so on the average the electrons in that particular principal quantum shell will spend its time further away from the nucleus as compared to an electron found in principal quantum shell 4. Okay, so that is the kind of correlation you need to think about. We are looking at the probability of finding electrons within a given space. Okay, and the larger your principal quantum number is, the time the electrons spend in that region, okay, further away from the nucleus is higher. Okay, so in this case, I think the last statement summarizes it all. The further away the electrons is from the nucleus, the weaker the attractions. We are talking about the electrostatic attractions between the outermost electron and the nucleus. There's also another idea you need to be aware of, that is effective nuclear charge. Okay, you'll notice that there is an additional word in front, that is effective. So we are not talking about nuclear charge alone, we are talking about the effective nuclear charge, which means it is the net nuclear charge explained by the outer electrons. Okay, so it's dependent on 2 factors as summarized over here. The first factor is obviously the actual nuclear charge. Okay, so of course if you look at carbon, okay, so let's look at the periodic table. If you look at carbon versus say neon, yeah, so neon will have 10 protons in the nucleus, carbon will only have 6 protons. So obviously neon will have a greater nuclear charge as compared to carbon. Okay, but there's another factor that comes in, that is the shielding effects, or sometimes we call it the screening constant. Yeah, but over in our lecture series, we'll be focusing on the term, or we'll be using the term shielding effect. Okay, that is represented by S. Right, so it is the presence of the inner electron shell that reduces the electrostatic forces or attractions. Why is that the case? Because electrons repel each other. Yeah, so if there are a greater number of inner quantum shell, the electronic repulsion exerted by these electrons on the electrons in the outermost shell increases. Yeah, so that means that it is a bit like the electrons in the inner quantum shell is pushing the outer electrons away, whereas at the same time the nuclear charge is trying to attract these electrons towards the nucleus. Yeah, so that achieves a balance, and this balance is known as effective nuclear charge. Yeah, the balance in a sense, it is the net nuclear charge experienced by the outer electrons. Yeah, so in short, we have this little equation over here. So effective nuclear charge is equal, or maybe to be more exact, effective nuclear charge is approximately equals to the nuclear charge minus of the screening constant. Okay, yeah. So we have a statement over here. Electrons in the same quantum shell do exert some shielding effect on each other. Okay, what do we mean by this? So for example, we are aware that, let's say, for carbon, we have electronic configuration 1s2, 2s2, okay, 2p2, right? Okay, yeah. So normally in the language of atomic structure, in this sense, we will say that these 4 electrons, okay, in the second principal quantum shell, they are shielded by the electrons in a 1s subshell. Okay, yeah. And normally we say that electrons in the same principal quantum shell have minimum shielding. Yeah, you notice the word I use here is minimum shielding. They do repel each other, but minimally. Yeah, so that is why these statements come into play. Electrons in the same principal quantum shell exert some shielding on each other. Yeah, remember that the nature of shielding is electronic repulsion. Okay, but the shielding exerted by the electrons in the same principal quantum shell is minimal, and the value is much lesser as compared to those experienced by or exerted by the electrons in the inner quantum shell. Yeah, that is something you need to be aware of. I use the term inner quantum shell, electrons in the inner quantum shell. You can also use this particular term that appears in your lecture notes, that is inner core electrons. Yeah, so there are a few terms, you can use them interchangeably, but just make sure that you are consistent in your writing. Okay, yeah. Then for section 4.1, we have trend in atomic radius. Okay, first of all, let us take a look at figure 13. These are the values taken from either the data booklets or some of the resources we have online. So maybe let me just point you to where you can find the information from your data booklets. Okay, so we are at the last page, which is the periodic table. So I'll just move up to section 5, atomic and ionic radii. Okay, so you might be wondering why are there two variables here? So you have a single covalent and then a van der Waals. Okay, so maybe let me explain a little bit. So the difference between the two is that, for example, when hydrogen forms a covalent bond with each other, so my apologies, I have to represent it with a circle. So imagine that these are the atomic valence electron cloud of hydrogen. So when they overlapped, so let's say we are able to find out roughly where is the middle of the electron density. That is the region where you have the highest probability of finding the pair of electrons, although this is not entirely correct, but just take it that it is about there. Okay, and then I also try to locate where the nucleus of hydrogen is. Okay, so this distance, okay, is what we call the covalent radius of hydrogen. Okay, but we will still call it the atomic radius because there is kind of like no way for you to find out what exactly is the radius of an atom. So we use the hydrogen H2 molecule as a proxy. Yeah, so essentially this is the atomic radius we're talking about, but to be more specific, we call it the single covalent radius. Okay, if you want to be more explicit, but in general, I think at the H2 level we don't have to be so explicit. Okay, then what about van der Waals radius? Okay, so van der Waals radius, you know, all of us know that most of the noble gases, for example helium and neon, they do not form covalent compounds. Yeah, so in that sense, how do we approximate their van der Waals, or how do we approximate their so-called atomic radius, where it's actually known as van der Waals radius? So again, same thing. So imagine this is a helium atom, and then there's also another helium atom nearby, and based on what you learned in secondary school, you know that they form some form of instantaneous dipole-induced dipole interaction, or later on in H2 under chapter 2 or topic 2, you learn it as dispersion forces. Okay, so they form a dispersion forces, so we can decide on the proxy of so-called atomic radius by again taking the distance from nucleus to around the middle of these two atoms. Okay, so around here. Okay, so I'm going to just draw a line between the two. Draw a line. Yeah, so in this case, this is the van der Waals radius. Yeah, so we will use this value as a proxy to the atomic radius, although it's a poor proxy. Yeah, but you can see that for some reason it is up in your data booklet. So you might want to be a little bit careful how you use these values. Yeah, and then you might find this term metallic over here. Yeah, so lithium atom, again, as you know, lithium kind of like difficult to have an atom, right? So we normally take the measurements by basing it on the solid state where it is in. It's actually a solid state atom where they are, the whole metal piece where all the atoms are very close to each other. So again, we take a proxy of the metallic distance between the two center portion, and then we just use that to call it the atomic radius. Okay, so do remember that all these are proxy, so just be very mindful what are the values you are using. I think for ionic radius, it is pretty straightforward. So basically, it is the distance between the nucleus and the outermost electron shell. So it is either you remove electrons or you gain electrons. I think that is straightforward. So that one, you probably don't need a lot of explanation on that. Okay, another source of reference you can use, because the data booklet, if you notice, it does not provide you with too many information. Okay, so what you have is, in this case, is only lithium and sodium. Okay, if you move down, there isn't other information. For group 2, yes, there is a bias towards group 2 because group 2 is directly in your curriculum, outlined in the syllabus document. If you're interested, you can take a look under physical periodicity. Yeah, there should be a group 2 chemistry over there. Okay, yeah. And of course, group 17 as well. And the transition metal. Transition metal is the last topic I think I mentioned in the earlier chapter. Okay, and that's about it. So there's limited information. So some of you might be wondering, what if I need reliable information on atomic radius or ionic radius or ionization energy, something you're going to learn later on. Where do you look out for this information? Okay, so you can go to this particular web page known as webelements.com. Okay, so webelements.com. Once you are on the first page, right, or the content page, you will see there's a large periodic table. So what you can do is you can just click on any element that you like. So for example, in our case here, let's look at lithium. So I'll just click lithium, and then when I click lithium, it will bring me to the page to showcase quite a lot of physical constants of lithium. So for example, over here you can they tell you the color, the classification, the standard state. I think the standard state is also important at 298 Kelvin because later on there's a chapter on energetics and thermodynamics. You will also learn a lot of definition based on standard states. You also hear you also read some description, and then you are given density, etc. So of course the information on atomic radius, it's actually over here. You can see 145 picometer. So 1 picometer is 10 to the power minus 12 meters. It will be good for you to know this particular units. Yeah. Okay, yeah, and then there's a lot of other information. So this is 145 picometer. So I can just click back and then go on to sodium, and then sodium is, if I just move down, 180 picometer. Yeah, so the information here are actually quite accurate. Yeah, so if you are really interested, you can even have all the ionization energy information. Yeah, so this is a very, very comprehensive website. Yeah, and it's trustworthy, so you can use this website for your own research. If you need to plot any graph just for your own leisure, like for example the trend in first ionization energy or ionization energy down a particular group, feel free to use the data here. Yeah, so in some of the examples I'm going to use in the future, I will also be using examples from this particular page. Okay, yeah. So next, I'm just going to go back to the lecture notes. Yeah, so this, in case you're wondering how figure 13 is obtained, yeah, so this is how the values are being obtained. So they are not fictitious, they are actually values that we obtain from reliable source of information. Okay, so now let's return to the lecture proper. So now you know that it's given to you that for the general trend, the atomic radius increases down the group. Okay, so you can see that it increases down the group. Yeah, it might be a little bit surprising for you. I'm not sure, because you might be wondering okay, so for example, as you move down the group, right? Okay, so if you're wondering what group we are talking about, so maybe I will just go to the periodic table. Okay, so if you look at group 1, right? If I go down to group, right, there is an increase in number of principal quantum shell. So from 2 in lithium, then 3 in sodium, 4 in potassium, 5 in rubidium, 6 in cesium, right? Yeah. So the number of inner quantum shell actually increases as well. So the increase in relative distance of the valence electrons from the nucleus actually increases. Okay, so I think it's written over here. Electrons are in general located further and further away from the nucleus. Yeah. And in our case here, the nuclear charge also increased. I hope you can agree with me on that. How do we know that the nuclear charge increased? Well, I mean, you look at the increase in atomic number. So lithium has 3 protons, sodium 11, then all the way to cesium 55, francium 87. Yeah, so the nuclear charge actually increased. But you also notice that the shielding effect, okay, the shielding effect also increases, right? Are we agreeable on that? So the increase in nuclear charge and shielding effect actually both increases together. Yeah, but in this case, so what are we expecting? Are we expecting the effective nuclear charge to change? Okay, so in this case, effective nuclear charge, right, is approximately equals to the nuclear charge minus the screening constant. Yeah, so because both the nuclear charge and the shielding effect increases, so you expect that the effective nuclear charge actually stays relatively invariant, or it doesn't change a lot down the group. Yeah, so in that case, are we expecting the size, atomic size, to remain the same? No, right? Because you know that from experimental result actually increases. So therefore, the more important factor to consider here is actually the increase in number of principal quantum shell. Yeah, so the increase in number of principal quantum shell actually leads to a bigger and bigger atoms. And of course, obviously, the principal quantum shell, you cannot squeeze them together because of electronic repulsion between the electrons. Okay, so the increase in principal quantum shell is a key consideration in explaining why the atomic radius increase. Yeah, in terms of effective nuclear charge, it should be relatively invariant. Okay, then the next portion we're going to look at is this, which is also important, and we kind of like plot a graph for you based on figure 14. Yeah, so atomic radii of period 2 and 3 elements. Okay, so if I may simply just highlight one of the key observation, right? So if I go to the periodic table, I focus on period 2 from lithium to neon, right? So I'm just going to highlight for you. Okay, so from lithium all the way to fluorine, and then of course neon, it went up lah. Okay, I'm going to leave neon aside first, so later on I will explain, or you might already heard my explanation earlier on. Then sodium all the way down to chlorine. Yeah, so what is the trend that you observe? You notice that in general, atomic radius decreases across the period. Yeah, I think you can easily explain why this is the case based on this particular relationship. Yeah, so again, as we move across the period, the nuclear charge actually increase, so we are agreeable on that. Okay, but the screening constant, or the screening effect, remains relatively constant. Yeah, if you look at what we have earlier on, right, the screening effect should change slightly. Okay, I can't exactly. Okay, it's over here. Yeah, over here. I think let me just highlight. Electrons in the same quantum shell do exert some shielding effect on each other. Okay, but it's just a little bit. Okay, so normally this little bit of shielding effect, right, we just say that the shielding constant, right, remain relatively constant or relatively invariant. So I'll just put like that. Okay, of course, you can also argue that the increase in nuclear charge outweighs the increase in shielding effect. That is perfectly fine as well. Or you can say it greatly outweighs the increase in shielding effect. So no problem as well. So in that case, the effective nuclear charge increases. That leads to a great decrease. You can see that the atomic radius actually decreases drastically across the period. And then there is something atypical here, and you might be able to tell me why already. Why is it that neon and argon suddenly shot up? Okay, so we already explained earlier on. For neon and argon, we are looking at van der Waals radius. So this is neon and this is argon. We are looking at van der Waals radius. We are not looking at atomic radius. So we are comparing apples and oranges. So there's no point in comparing. The explanation is given here. Okay, so if you are interested, you can read about it. But basically, in general, there are stuff which I already mentioned to you earlier on. Okay, and then the 4 bullet points here I have already explained. Yeah, so maybe let me go through. So nuclear charge increases across the periods. Okay, shielding effect remains relatively constant, relatively invariant, or you can say that the increase in nuclear charge greatly outweighs the increase in shielding effect if you wish to lah. And then effective nuclear charge increases generally across the period. So if you want to conclude in that sense, you can, but I mean, it really depends. You can conclude by saying that therefore the outermost electrons are put closer to the nucleus. So the attraction of the outermost electrons towards the nucleus becomes stronger. So therefore it leads to a decrease in atomic radius. Okay, yep. Then for first row transition elements, you notice that the atomic radius remains relatively invariant. We will revisit this when we are talking about transition metal chemistry. Yeah, so if you wish to, you can wait until then, but of course over here we gave you the explanation. So although there's an increase in nuclear charge, okay, the electrons are actually being added to the inner 3D subshell. So and this actually contributes to shielding effect. Okay, so in that sense, your shielding effect is effectively nullified. Okay, and therefore the nuclear charge remains relatively constant across the transition element. But this is not always the case lah, if you notice. Yeah, so you notice that there is still some variation over here. Okay, so maybe let me just circle it properly. There is still some variation. If you want to understand the nitty-gritties, I'm afraid that H2 cannot give you a perfect answer. You really have to understand, maybe go on to the university level, maybe read more. That might give you some explanation. As to the really 100% foolproof explanation, I'm afraid that in most cases it's difficult to find the answer. Okay, so over here the reasoning we are giving you is just sort of an excuse or sort of like an observation and explanation that we put in to try to explain the phenomenon. Okay, so again, to try to explain the phenomenon, not so much as to tell you that this is actually the gospel truth. Okay, yep. What about the ionic radius? The trend in ionic radius under 4.2. Okay, so under 4.2, we have to be very careful what we are talking about. Are we talking about anion or are we talking about cation? Yeah, so many a times when you're working through your tutorials or your in-class exercise, you really need to read through the questions, or you need to have at least a very basic knowledge in what you are dealing with. Okay, so once you are clear, then everything else will be straightforward. So for example, in our case here, we're all dealing with cations from sodium plus all the way to silicon 4 plus. Okay, and then for P3 minus all the way until Cl minus, we are dealing with anions. Okay, so we need to be very clear. And once we are very clear, then we need to check. Okay, so we are dealing with anion, right? So therefore, let me just go to the periodic table. Therefore, right, for P3 minus, S2 minus, and Cl minus, in our case here, we are looking at an argon electronic configuration. Okay, so they are isoelectronic to argon. Okay, so we're looking at argon here. Okay, so therefore, the number of principal quantum shell is 3. Okay, so we are saying that P3 minus, S2 minus, and Cl minus are isoelectronic with argon. Okay, then what about sodium plus all the way until Si4 plus? Okay, so for sodium plus with Si4 plus, we are actually looking at the element before that. We are looking at neon electronic configuration. Okay,
Yeah, so they are isoelectronic with neon, so it only has two principal quantum shell. Okay, so because of that, argon has one additional principal quantum shell as compared to neon. So in general, we are expecting the n ions to be larger than the cations. So this is a no-brainer, right? You can conclude based on that. Similar idea, I think you can apply based on the trend in the atomic radius down group 1. Okay, so in that case, we successfully explain why in general anions are bigger than cations when we are looking at the trend across period 3. Okay, however, we need to explain a little bit more why is it a decreasing trend. You notice that in our case here is actually a decreasing trend. Okay, I think this is again straightforward because we are looking at effective nuclear charge, which is approximately equals to the nuclear charge minus the screening constant. Okay, so in this case, my nuclear charge actually increases from sodium all the way to chlorine. Okay, so sodium have 11 protons, magnesium 2 plus 12, aluminum 3 plus 13, silicon 4 plus 14. Okay, then what about the screening constant? The screening constant, if you notice, right, is actually fixed. Do you notice that it's fixed? It is actually the neon core. So the first two principal quantum shell. So because I have a fixed screening constant, but the nuclear charge increase, so across the cation series, the effective nuclear charge increases. That leads to a decrease in cationic radius because the outermost electrons are attracted more strongly towards the nucleus, right? So that is how we are able to explain this. Okay, so I'm not going to bore you the details by going through the explanation, but you can go through them on your own. Okay, they are written out nicely in your lecture notes. Okay, so yeah, and of course the part which I highlighted to you at the beginning over here, there's a sharp increase in ionic radius from the cationic series to the anionic series because of the additional principal quantum shell. Okay, so just remember how to position your answer. Okay, then I'm going to move on to the next portion or the next section, the final section, which is on ionization energy. Ionization energy is a term that is unfamiliar to most, if not all of you. Okay, so before I go into any further discussion, it will be good to focus on the definition. Okay, so make sure you understand every single word used and perhaps, if possible, able to recite every single word from here. But of course, once you understand the term, then you do not need to memorize the definition. Okay, so let me reiterate that once you understand the term, you do not need to memorize the definition. Okay, so first we need to understand what is first ionization energy. So it's the energy needed to remove 1 mole of electrons, this is important, 1 mole of electrons from 1 mole of gaseous atoms to produce 1 mole of unipositively charged gaseous ions. Yep, so this is the exact definition, and of course by definition the term is endothermic in nature. Okay, so it is the energy required or energy needed to remove 1 mole of electrons. Okay, and blah blah blah. Right, so when you are writing out the definition in terms of chemical equations or in terms of balance equation, this is how it should be like. Okay, so make sure you have a first IE somewhere, first IE of X in this case. Okay, so it will be good for you to indicate what you're dealing with. So to be more exact, for example, for gaseous sodium to give me 1 mole of unipositively charged sodium cation and 1 mole of electrons, it will be good to define this as first IE of sodium gaseous. Okay, so you'll be good to write a gaseous over there. Yeah, so using the same idea, the second ionization energy is the energy required to remove 1 mole of electrons from 1 mole of unipositively charged gaseous cations to produce 1 mole of gaseous ions with double positive charge. Okay, so by definition, it is like this. Yep. So there is often a misconception when students thought that the definition for second IE is like this, like this, 2 plus gaseous plus 2 electrons. Okay, this is not the definition for second IE. Okay, so if this is an energetic term called A, right? So A will be equals to first plus second IE of X. Okay, so be very clear what is going on here. Okay, yeah, so I think the rest I do not need to go through. You can read them through on your own. And of course, the larger the number of principal quantum shell, the further the electrons is away from the nucleus. And because they experience a weaker nuclear attraction due to the smaller effective nuclear charge, I expect a lower first IE. Okay, and of course, effective nuclear charge plays a very important role. Okay, yeah, so for section 5.2, what is important here is we need to look at the trend in the successive ionization energies of the same element. Okay, so for the same element, ionization energies always increase in the following order. Yeah, this is inevitable. Okay, so the first IE is always smaller than the second IE. The second IE is always less endothermic than the third IE. Yeah, this is definitely the case if you try to think about this idea of effective nuclear charge is approximately equals to nuclear charge minus the screening constant. Yeah, because for every electrons I am removing, I am kind of reducing the screening constant. Okay, do you take note of that? Do you realize that I am reducing the screening constant? And because of that, the outermost electrons experience a stronger and stronger effective nuclear charge. Okay, so I think the full explanation is given here. You can read through them. Okay, and then of course the next part is we need to apply successive IE values. This satisfies two learning objectives, J and K. Okay, so this objective directly requires you to deduce the electronic configuration of elements from successive IE data. Okay, so this is pretty straightforward, so we will analyze them later. And then we are required to interpret successive IE data of an element in terms of position of the element within the periodic table. Okay, so first of all, let us take a look at the example given here. We are given the electronic configuration of magnesium, which is 1s2, 2s2, 2p6, 3s2. Okay, so I will highlight the inner quantum shell, which is principal quantum number 1 and 2. Okay, so you notice that I'm going to circle the 3s2. You notice that the amount of energy required to remove them is the lowest. Okay, and then you notice that there is a small gap over here. Okay, yeah, so and then after that, this is followed by all the way from 2p, and then of course there is a little bit of a gap, and then after that the 2s. Okay, and then for the inner quantum shell is 1s. Okay, I think you can easily understand this because first of all, the relative distance of the electrons found in the 3s orbital is at the furthest distance away from the nucleus. Yeah, so in that sense, they experience the weakest effective nuclear charge. Yeah, so they are the most easily removed. Okay, and then as we move on to principal quantum shell 2, the inner quantum shell is only 1s2. Yeah, so from there I expect a gradual increase from the 3rd to the 10th IE. Yeah, because they are being removed from the same principal quantum shell. And remember that we need to use this formula. We need to often use this particular relationship for us to discuss. Yeah, as I remove more and more electrons, I am reducing the screening constant, and that will balloon up the effective nuclear charge. Okay, yeah. So there will be a great increase. Okay, in this case, a slightly great increase from 8 to 9th IE. Why is that the case? Because on the average, the electrons in the 2s orbitals, right, are on the average closer to the nucleus as compared to that in the 2p. Okay, why is that the case? Okay, so if I'm going to draw the axis out like this, okay, yeah, so this is x, this is y, and this is z, right? Yeah, so on the average, if you are looking at the s orbital, it's spherical in shape. Okay, so I'm not drawing a very nice sphere here. Okay, then on the average, if we look at the 2p, we are looking at a figure of 8. Yeah, so if you look at the bulk of the electron density, where the electron densities are being concentrated, on the average, electrons in the 2s orbital spend its time or their time closer to the nucleus as compared to that in the 2p. Yeah, so this is the origin of this particular definition. Okay, I mean this particular explanation, what am I talking about? Okay, so it's explanation, not definition. Okay, sometimes you can also look at it from the perspective that because all the 2p electrons are already being removed, yeah, so therefore now the effective nuclear charge, okay, is greatly increased, because now I am only left with the 2 electrons in the 2s subshell. Yeah, you can use the explanation as well, but in general we tend to look at an explanation based on the relative distance of the electrons in the 2s versus that in the 2p. Okay, yeah, it may not be the 100% gospel truth, it doesn't really matter here, but I think by and large we are comfortable with this idea of explaining. Okay, and of course the final bullet point, there is a huge jump from the 10th, okay, so the 10th electrons, so this is the 10th electrons over here, to the 11th. Why is that the case? Because right now I am removing the last two, the 11th electrons, and it is found in a 1s orbital, and that 1s orbital directly experience the almost complete nuclear charge, okay, from the nucleus. So in terms of distance or in terms of effective nuclear charge, it experienced one of the strongest effective nuclear charge, and the only shielding the 11th electron is getting from is from the 1s electrons that is being paired up with. Okay, so therefore why are we talking about this? Yeah, because if you look at learning objective 1J, students are supposed to deduce the electronic configuration from the successive IE data, right? So based on this data, if I'm telling you that I have an element with 12 protons, and this is the these are all the 12 electrons, you should be able to write me the electronic configuration. Okay, so that is the reason why for learning objective 1J, and that is the reason why we provide you with figure 17 as an illustration. Okay, yep. Then moving on to exercise 5.1 as a work example. Okay, let's see how we can apply it. So we are supposed to identify the group number of the element for each set of ionization energy. So this is the first IE, right? Okay, so right now I'm going to just highlight, okay, over here. Okay, so we are looking at, can you see that 1, 2, 3, 4, 5, 6, 7 all the way, and then there is a little bit of a jump here from 7th to 8th. Okay, so I'll just leave it as a I'll leave a gap, and then blah blah blah, and then of course the huge jump occurs here. Okay, so because of this we are looking at this portion. Okay, so therefore the answer is group 17. Yeah. Okay, yeah. Then for B, successive ionization energy is in this particular order. So we have 10, 60, 1900, 29, 20, 49, 60, 62, 80, and then you can see that there is a huge jump over here from 6280 to 21,200. Yeah, so this is a huge jump. So it is quite safe to say that these are the outermost electrons. So there are 5 in total, so we are looking at group 15. Okay, so B is in group 15. Okay, and then for C, successive IEs, 6, 87, 15, 77, 32, 32, 43, 55, and there's a huge jump, 16091. Okay, so we count the total number of electrons here. There are 4, so therefore group 14. Yeah, so normally we look out for where the largest jump occurs. Yeah, so that is the simplest way for you to work on. Okay, next we have exercise 5.2. So the use of the data booklets is relevant to this question, so therefore you need the data booklet. So we need to come back to the data booklet. We don't know where to use. Oh, before I move on, I thought it's good for me to share with everyone where to find the data for the ionization energy. So they can be found under section 2. Okay, so it spans 3 pages. So section 2, you have ionization energies. You are only given the first 4 IEs, just take note of that. And then you are given all the way until elements 38, so that is strontium. And then after that you are given some other elements, for example silver. For some reason I'm given silver, and then tin, and then indium. Okay, and that's about it. Yeah, so oops, not 3 pages, 2 pages. So you have 2 pages worth of ionization energy data. Okay, yep. So for 5.2, the successive IEs in kilojoules per mole of an element X given below. So you are asked what is X. Okay, so first of all, we go through the same logic. Yep. So we look at 870, okay, 1800, okay, 3000, 3600, 5800, okay, and then 7000, and then you notice that there is a break. Okay, so there's a break over here. Yeah, so let us count how many electrons are there. So there are a total of 6 electrons. Yeah, so because there are 6 electrons, we are looking at group 16. Okay, so over here we're looking at group 16. Okay, so we need to look at a periodic table. Okay, so maybe periodic table is a better tool over here. So we look at a periodic table. Okay, so we'll just erase all the non-essential data first. Okay, so we need to look at group 16. Okay, all these possible answers: oxygen, sulfur, selenium, tellurium, polonium. Okay, so we have tellurium over here. Okay, cannot be zirconium. Okay, because this is a transition element. It can't be arsenic as well, because arsenic is group 15. Okay, so this is wrong. Zirconium transition element, it is not relatively invariant, so no. Iodine, what about iodine? Nope, it's not iodine. So the only answer here is tellurium, because tellurium is in group 16. Yeah, so there's only one answer here, so not very inspiring, because you have to be a little bit careful, because some question they will give you 2 answers that are in group 16. So you need to differentiate them a little bit by looking at the ionization energy data provided on those 2 pages I mentioned earlier on under section 2. Okay, because for this question it's not mentioned, so I do not need to discuss them for the purpose. Okay, so if you chance upon them in your tutorials or your in-class exercise, I think we can do further discussion. Yep, so next we are looking at section 5.3. Okay, so we have a learning objective: explain the factors influencing the ionization energies of the elements. So we need to refer to data booklets. Okay, so we're looking at trends in ionization energy of different elements. Okay, so again, we're looking at down the group. Okay, from lithium all the way to cesium. Yeah, so this is the same explanation. So ionization energy decreases down a group. Okay, why is that the case? Yeah, as I mentioned earlier on, because the valence electrons, okay, due to the increase in principal quantum shell, the valence electron in cesium is at a much further distance away from the nucleus as compared to that in lithium and sodium. Yeah, so because of that, they are being attracted less strongly. Okay, then you notice that there's a little bit of a conclusion over here. Both the nuclear and shielding effect increases, so effective nuclear charge is relatively invariant. Yeah, so the principal quantum shell, so the increase in number of principal quantum shell is a more important factor in deciding how the electrons, or how much energy is required to remove that particular electrons. Yeah, so due to the weaker electrostatic forces of attraction, I require less energy to remove the first electron from cesium as compared to that in lithium. Okay, and then of course across period 2 and 3 will be quite interesting. Okay, so perhaps let me just focus on period 2 for illustration purposes. Okay, so for period 2 we have lithium, beryllium, and then we have boron, carbon, nitrogen, and then oxygen, fluorine, neon. Okay, and of course I'm going to highlight using another color. Period 3, same thing. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. You'll notice the general trend. The general trend is an upward trend. Do you notice it's an upward trend? Can we understand why is it, or can we explain why is it an upward trend? I think we can understand that quite easily, because in general across the periods, nuclear charge increase, but the shielding effect remains relatively constant, or you can say the shielding effect increases just by a little bit. So in general, across the period, so we need to understand that across the periods, effective nuclear charge increases. Yeah, so that explains why there's a general upward trend. But you also notice that there is a break along the way. So for example, beryllium, boron, that's between group 2 and group 13, same as magnesium, aluminum, there's a break. And then of course there's another break. Let me just use another color, maybe I use yellow. Nitrogen, oxygen, that is group 15 and 16, and then phosphorus and sulfur as well, that is group 15 and 16. Yeah, why is there such a trend? Yeah, so we might want to look at the electronic configuration from here. So if you look at lithium, I'm going to write down the valence electronic configuration. Okay, so lithium is 2s1, beryllium, I'm going to write beryllium is 2s2. Okay, 2s2, and then for boron will be helium electronic configuration 2s2 2p1. Yeah, so again, what do you notice? You notice that I am going from 2s to 2p. Yeah, so if you compare boron and beryllium, on the average, the electrons being removed in boron is in the p orbital. Yeah, that's on the average. It spent its time further away from the nucleus as compared to that in S. Yeah, so therefore the first IE actually decreases by a little bit. Okay, you can also look at it from another perspective. You can look at it from the perspective that the effective nuclear charge experienced by the 2p electrons is smaller as compared to that experienced by the 2s electrons in beryllium. Why is that the case? Because the increase in shielding effect here outweighs the increase in nuclear charge. You can also explain it based on that. Yeah, because remember that for effective nuclear charge is approximately equals to the nuclear charge minus the screening constant. Yeah, we kind of expect the effective nuclear charge to increase steadily across the period. Because the screening constant, you assume that it increases slightly, and the slightly will be the same in terms of magnitude. That's an assumption. Yeah, but between beryllium and boron, the increase in shielding effect becomes more apparent. Why is that the case? Because there is a filled 2s subshell. Yeah, so you can look at it by looking at the fact that okay, now there is some sort of like an inner core which is 2s, and then the 2p, the electron spend its time sort of further away from the nucleus. Yeah, so the electrons in the 2p subshell or orbital spend its time further away, so attracted less strongly, or you can say that it experience a greater shielding effect. Yeah, so any of these explanation will work. Okay, yeah, so I think the explanation can be found over here in the next page on the anomalies. I think the 2p, the 3p versus 3s, 2p versus 2s is found over here. So you can read through them at your own leisure. Okay, and then the other anomalies will be between group 15 and group 16. So we'll look at nitrogen over here. So for nitrogen, the electronic configuration is helium core 2s2 2p3. Okay, for oxygen will be helium core 2s2 2p4. Okay, yeah, so over here I'm just going to sketch out the 2s. So 2s, this is 2s, and then 2p. Okay, so you notice that for nitrogen the 2s is filled, the 2p orbitals are all singly filled, and then for oxygen it paired up. So this is the first instant of pairing. This is the first instance of pairing. Okay, so the first instant of pairing will also result in a greater increase in effective nuclear charge due to the inter-electronic repulsion. Okay, so I think it's written over here. You can read through them. So the inter-electronic repulsion between the first instant, the first paired electron in the 3p subshell, okay, will result in a slight dip in the first IE. Okay, so do remember this. This is the main idea you have to be familiar with. Okay, so in summary, in short, across the period, regardless of whether is it period 2 or period 3, effective nuclear charge increases. The general trend in first IE is an increasing trend. Yeah, but there are anomalies as well, or there are short dips. Yeah, so that's between group 2 and group 13 and group 15 and group 16, and the explanation has already been given in detail either in your lecture notes or in my earlier explanation. Okay, so in summary, for the first explanation, it is because on the average, electrons in the 2p or 3p orbitals spend its time further away from nucleus as compared to electrons in the 2s or 3s orbitals. Yeah, so that result in a smaller effective nuclear charge being experienced, and therefore lower first IE. Okay, then between group 15 and group 16, we look at the first instant of pairing, which result in inter-electronic repulsion between the paired electrons. Yeah, so that also result in a lowered amount of energy required to remove the electrons, the first electrons to be removed. So therefore, results in a dip in the first IE. Okay, yeah. So it's a lot of words here, but if you understand or if you listen to my explanation, you can get the gist of the story. That will be fine. Okay, for transition elements, it's a little interesting. So that's learning objective from topic 13. So you need to explain why atomic radii in first IE of TM are relatively invariant. So that's over here. Okay, so again, the main idea is here. The first electrons or the first IE involve removing electrons from 4s. Okay, and then second bullet point, nuclear charge increase due to the number of protons. Additional electrons are added to the inner 3D. Yeah, the inner 3D results in shielding effect, but because the 3D orbitals, okay, because the 3D orbitals, right, is quite diffused. Yeah, so this increase in the shielding, right, kind of nullified the increase in the protons. Okay, so you have you have electrons being added to into the 3D subshell. Okay, they act as the core to shield your 4s, and then as I add more and more electrons, the shielding actually kind of increases, and at the same time the nuclear charge increase as well as we go across period 4 along the transition metal series, the first 3D 3D element series. So that will be the first row transition element, scandium, titanium, vanadium, etc. Yeah, so because of that, the shielding effect will nullify the increase in the nuclear charge. So that result in effective nuclear charge remains almost invariant. Okay, yeah. So therefore, energy required to remove the outermost electrons remain relatively invariant. Yeah. So this might be the idea that you need to take away with. Okay, we will revisit this under our last topic for transition metal chemistry. So that will be next year May. Okay, so you can just keep in view of this idea at the back of your mind as you revise atomic structure, but do bear in mind that you have already gone through them under atomic structure. Okay, then over here we have exercise 5.3. That is a work example. Okay, so what you have here is the elements in the first 4 periods. Okay, so question you are being asked is, which element in the diagram has the largest atomic radii? Okay, so this seems to be quite a difficult question. Of course, the simplest answer you can come up with would be look at the data booklet. Okay, and then just look at the trend and then find the data, because some of you might be wondering, okay, can I actually turn to page over this page and then I look at all this data and then try to find the answer? Yeah, of course, this is not the wisest way of doing. Yeah, but in general, we want to look at the elements with the largest atomic radii. Okay, so now first of all, we should look for answers by looking at the largest periods, or the period with the largest number. Okay, so this is period 1, period 2, period 3, period 4. Okay, so we should be looking at period 4. So the rest will not be looking at them. Yeah, so across period 4, what did we discuss earlier on? Across period 4, electrons are being added to the 3D. Okay, so over here we're adding electrons into the 3D. Over here we're adding into the 4p. Okay, so across the period, electrons are being added into the respective subshell. Okay, but remember this, effective nuclear charge actually increases across the period. Okay, so effective nuclear charge is nuclear charge minus screening constant. Yeah, so the screening constant stays relatively constant. Okay, not exactly constant, but relatively constant. The nuclear charge increases drastically. Yeah, so effective nuclear charge increases across the period. So because of that, I expect the elements with the largest atomic radii to be found on the left. Okay, so amongst all the options, I'm not going to choose krypton because that we are looking at van der Waals radii. We are not going to choose scandium. Bromine, obviously no, so we are only going to choose potassium. Okay, so where if you are in doubt, you may want to revisit the earlier the earlier section of the video lecture. Okay, I believe this is the last example, exercise 5.4. So question, you see this extremely important statement, so do take note of this statement. The use of data booklet is relevant to this question. So the bar chart shows some information about the first IE of elements numbering from 1 to 4. The elements are adjacent to each other in the periodic table, so this is very important. They are next to each other, adjacent to each other, with increasing proton number. Okay, so if this proton number is n, this is n plus 1, this is n plus 2, and this is n plus 3. Okay, so question asked is what could this element be? Okay, so if you look at option A. Okay, so for option A, we are looking at boron, which is in group 13. Okay, so we're looking at boron, carbon, nitrogen, and oxygen, right? So you know that for boron is an increased trend, boron, carbon, nitrogen, and then oxygen, there's a dip, right? Yeah. So over here, there's no dip. So obviously this is incorrect. Okay, for option B, we are looking at transition element for cobalt, nickel, copper, zinc. Okay, so we know that transition elements they remain relatively invariant, cobalt, nickel, copper, zinc, but you notice that the fourth element is quite high. So if you wish to, you might want to check out the IE data, which I showed you earlier on. Okay, so you can look at the IE data if you wish. Okay, over here, and then we will look at cobalt. Cobalt is 757, nickel is 736, copper is 745, so they're quite similar. You notice zinc is 908. It's the highest amongst the four. Yeah, so this seems to be the answer, right? So I'll just put a tick next to it. Okay, I'll look at the rest of the option first. Okay, for C is magnesium, calcium, strontium, barium. As we know, as we go down the group, the first ionization energy decreases. So again, number 4 is the highest. So this is incorrect. Okay, and then what about silicon, phosphorus, sulfur, chlorine? Okay, so again, we can either look at this data or we can go to a periodic table. Okay, for silicon, phosphorus, sulfur, chlorine, again, it's the same thing. I'm expecting an increase, right? So silicon, phosphorus, I expect increase, and then sulfur, I expect a dip or a small dip, and then after that, chlorine, I expect a huge jump. Okay, but is that the case? That is not exactly the case, because in this case, it's not increasing. Okay, so this is not likely to be the answer as well. So because of that, I will choose option B as my answer. Okay, so that will be the end of the review of exercise 5.4, and that should be the end of the lectures as well. For the next portion, looking ahead, why are we learning atomic structure first? Because the incoming topic is on chemical bonding, which is extremely exciting, because chemical bonding is very fundamental in the learning of H2 chemistry and in all aspects of chemistry. So do stay excited, and do keep a lookout for the incoming lecture videos, okay, on chemical bonding. And of course, the most important idea that you might want to read a little bit more in advance regarding chemical bonding is on electronegativity. Okay, so we'll give you a glimpse on what electronegativity is. Okay, so it quantifies the attractive force of one atom exerting on the electrons over the other atom in a chemical bond. So a larger number means a larger force of attractions towards the electrons. Okay, so a very simple example I'm going to illustrate here will be HCl. So chlorine has a larger electronegativity value as compared to hydrogen. So therefore, the shared pair of electrons will be displaced towards chlorine. So chlorine will take on a permanent partial negative charge, and hydrogen a permanent partial positive charge. This has huge implication on the intermolecular force of attraction, which we're going to discuss under chemical bonding. Okay, so stay tuned, and I'll see you in the next lecture.